My name is Jitan. Today I am going to explain about some minimum spanning tree algorithms. A minimum spanning tree algorithm of a graph is a subset of its edges that connects all vertices with the minimum total weights and no cycles. There are two main algorithms to find an MST, minimum spanning tree. They are Prim's algorithm as well as Kruskal's algorithm, second one. First we talk about Prim's algorithm. Prim's algorithm starts from an arbitrary node. Arbitrary node means from an predefined node and then expands the MST by always adding the smallest edge that connects an unvisited node. It uses priority queues, minimum heap priority queues. It is the most important one to reduce the time and space complexities to efficiently select the smallest edge at each step. This makes it efficient for dense graphs where the number of edges is high. The best time complexity is E of order of edges when graph is structured. Worst complexity is order of edges log V using minimum heap with an adjacent list. Space complexity is order of vertices plus edges. The second one is Kruskal's algorithm. Kruskal's algorithm takes a different approach by sorting all the edges based on weights and then adding them one by one, ensuring no cycles are formed. This is the most important one. No cycles will be formed. It uses union find to check cycles effectively. This algorithm is well suited for spare graphs where number of edges is relatively low compared to the number of vertices. Best case time complexity of Kruskal's is order of edges log v if edges are already sorted. Worst case is order of edges log e due to sorting edges. Space complexity is order of vertices plus edges. Okay, for sorting the edges list and union find data structure. Now let's talk about shortest path algorithms. Shortest path algorithms are used to find minimum distance from a source node to all the other nodes in a weighted graph. The two most commonly used algorithms are Dijkstra's algorithm and Bellman-Ford algorithm. Dijkstra's algorithm. First one is Dijkstra's algorithm. In Dijkstra's algorithm, it is a greedy approach that expands the shortest known path first using a priority queue. Priority queue is the most important in this. It ensures that the shortest path to each node is found efficiently in graphs with no negative edges weights. Best case time complexity for this Dijkstra's algorithm is order of V log V. That means vertices log vertices. If each node is processed once with limited edges. Worst case is order of V plus E log V in dense graphs with many edges. If the graph has many edges, the time complexity will be this. It is the worst case. And the space complexity is order of V plus E, order of vertices plus edges for storing the graph and priority queue. However, in Dijkstra's algorithm, there is a disadvantage that it does not work with native weight edges, making it unstable for real-world applications. So, there is another shortest path algorithm, that is Bellman-Ford algorithm. Bellman-Ford algorithm is an alternative to the Dijkstra's algorithm that works even with the native edges are present. It based on the relaxation technique where it updates the shortest path estimates over multiple interactions. It can also detect negative weight cycles, which the Dijkstra's algorithm cannot. Best case complexity is order of vertices O of V. Worst case complexity is order of vertices into edges, that is O of VE. When the algorithm needs to check every edge multiple times. This is the worst case. And the space complexity is order of V for storing distance values. While Bellman-Ford is more powerful in handling native weights, it is significantly slower than Dijkstra's algorithm for large graphs. This is the disadvantage for this. Now the conclusion. Prims and Kruskals are used for Finding minimum spanning tree with Prim being better for dense graphs and Kruskals for square graphs. The Dijkstra's algorithm is effective for finding the shortest path, but it fails with the negative weights, whereas Bellman-Ford is slower but handles negative weights and detects negative weight cycles. By understanding the best and worst case complexities, we can choose the right algorithm based on the structure of the graph, the problem constraints. Thanks for watching.